Hey everyone, welcome back. So last time we got our feet wet with Rust's basic data types. But, data's not much good if you can't put it somewhere, right? That's where variables come in. Today, we're going to dive deep into how Rust handles them, and trust me, it's all about working safely and super effectively. This whole explainer is brought to you by the awesome folks at Forge College. All right, let's jump right in.
Oh man, we have all been there. You're chasing a bug for what feels like an eternity, tearing your hair out, staring at the screen, and then bam, you find it. Some variable, way deep in your code, got changed when it had absolutely no business being changed. It is probably one of the most maddening, frustrating bugs you can run into, and it happens all the time.
Well, you can tell the people who created Rust felt that exact same pain, because they baked a really powerful solution to stop that kind of chaos right into the language itself. And it's not just a friendly suggestion, it's like a golden rule for handling your data. And the whole point? Safety and predictability.
Okay, so first things first, a quick little bit of terminology. We all say variable, right? But in Rust, the really precise term is a binding. Just think of it like this. It's a name that's tied or bound to a value. It might seem like a tiny difference, but believe me, it's super important for understanding what's coming up next.
And here it is, the big one, the golden rule. By default, every single binding in Rust is immutable. What's that mean? It means once you've given a name to a value, that's it. You can't change it, period. I like to think of it like a sealed blueprint box. You put your blueprint, that's your value. Inside, you close the lid, and boom, it's locked. You can look inside all you want, but you are not changing what's in there.
And the absolute best part, the compiler is like your personal bodyguard. So look, if we create a binding A and set it to 10, no problem. But the second we try to change A to 11, nope, the compiler just stops you dead in your tracks. It throws an error. This isn't a runtime bug. This prevents the bug before you can even run the code. That sealed box is working perfectly.
Okay, so you're probably thinking, but what if I actually need to change value? Don't worry, Rust has a tool for that. But, and this is key, it forces you to be super intentional about it. If you want a binding to be changeable, or mutable as we call it, you have to spell it out. You use the mute keyword. Think of it like this. You're creating a blueprint box, but this one has a special hinged lid. You're signaling to yourself and anyone else reading your code that the stuff inside is meant to be updated.
And the process is really simple, but it's totally deliberate. First, you declare your binding with let mute b equals 5. That's you saying, hey, this one can change. Now, because you did that, the binding b can be reassigned. So we can go ahead and do something like b equals b plus 7. We're just taking the old value, adding 7, and putting the new result right back into our hinged box. See? It's a conscious choice. It can't happen by accident.
All right, so mute is perfect for changing a value in place. Simple enough. But what if that's not what you want to do? What if you need to take a value through a series of transformations? Like you start with one thing and you want to turn it into something else, maybe even changing its type as you go. For that kind of job, Rust has another tool in its belt, and honestly, it's even more powerful.
And this is called shadowing. Now stick with our box metaphor. With mute, we open the hinged lid and change the contents. With shadowing, we don't touch the old box at all. Instead, we create a brand new box, put a new value inside, and slap the exact same label on it. This new box now kinda casts a shadow over the old one, so you can't even see the original anymore.
And here's where shadowing gets really cool. Because you're making a completely new binding, you're not just changing the value, you can change the entire type. That's a huge deal because it's something you absolutely, positively cannot do with a mute variable. This is what makes shadowing a tool for transformation, not just, simple mutation.
Let's look at a really practical example of this. It's super common. Okay, so we start with a variable s, that's a string, and it's got some extra spaces. First, we shadow it with let s equals s.trim. This creates a brand new s that's a nice clean string slice. But we're not done. We shadow it again with let s equals s.parse unwrap. And now we've created a third s, which is an integer. So think about that. 3 totally different variables, 3 different types, all using the same simple name, s. It's so clean and so much easier to follow than having s-string, s-trimmed, s-number. You get the idea. So let's just break this all down in one place. This table really sums it up perfectly. Your default let, that's your safety net. No changes allowed. Then you've got let mute. You pull that out when you need to change a value in place, right inside its box. And finally, shadowing, which also uses let. That's your go-to for transforming a value, especially when you need to change its type along the way. See?
3 different tools, each one perfect for a different job.
All right, let's move on to our next topic, unpacking your data. We're going to look at a cool feature called pattern destructuring.
So this is really powerful. You can basically pull apart a complex type, like a tuple, right in the same line where you declare your bindings. So check this out. We start with a simple tuple called pair that has a 1 and a 2 in it. Then, with just one line, let x mut y equals pair. We've pulled those values out and assigned them to x and y. But did you catch the really cool part? We applied mut selectively to just y. That means x is going to be immutable, locked down, but y will be mutable and ready to change. And just like you'd expect, the compiler enforces this perfectly. If we try to go and change x, nope, compiler error. It's immutable. But y? We can update y all day long because we specifically marked it as mut right inside that pattern. This just gives you this incredibly fine-grained, precise control over your data. It's awesome.
All right, let's wrap this up with a quick recap. Think of this as putting together your new Rust toolkit for variables. So here's what's in your toolkit now. First, you've got default safety. Everything is immutable unless you say otherwise. Second, when you need change, you're explicit about it with mut. Third, for those clean transformations, you've got shadowing, which even lets you change the type. Fourth, you can do precise unpacking with pattern bindings to pull data apart. And last but not least, always remember that scope, the curly braces, defines the clear boundaries for where a binding is even valid. So, why does any of this matter? Why all these rules? Well, these aren't just random rules someone made up. They're all designed to help you write code that is way safer, way more predictable, and honestly, just a lot easier to read. And when you're working on complex systems like, say, Solana programs, where getting it right is absolutely critical, having this built-in safety net is just invaluable. Trust me, your future self and your teammates will thank you for it.
This whole deep dive into Rust variables was brought to you by our friends at Forge College. If you're looking to learn more about Rust, Solana, or really any other topics for building in Web3, you should definitely go check them out at forge.college.
So there you have it. You've now got the tools to manage state in Rust in a way that's safe, clear, and super intentional. But of course, the next logical question is, what do you do with that state? How do you make your program actually act on it? Make decisions, repeat actions? Well, that is exactly what we're going to cover in our next explainer. Thanks so much for watching.